So let's go back. The tradition in chemistry is do a little bit of history. And the reason is that it's good to see the dead ends that people went down and what enlightenment brought them to something that we now know to be true. The problem was in the 18th century, up to the 18th century, the view of the world was largely mechanical. We had a situation where people thought of everything being F equals ma, right? Force equals mass times the acceleration. It was a Newtonian world. Newton had solved everything. Force. Usually we write it in newtons. We use the MKS system in this class. Newtons. So we'll just check this equation. Mass is in kilograms. Acceleration, meters per second per second. And Newton also worked out that work is just the force applied over a distance. Work, energy. And so joules is just obviously a Newton times a meter. See, I put these square brackets to mean units. Or if you multiply all that through, you get kilogram meter squared per second per second. So what does he mean by that? Well, the world that they knew was, take this glass, it stays still. I'm not applying a force. If I apply a force, an impulse, oh, it's not going to work. It'll roll along, right? And without friction, it won't accelerate after that. It'll just keep on rolling at a constant velocity. Of course, if I push it like this, it stops because of friction. And they knew that bodies at rest stay at rest until something is done. So even liquids. So if you put water in here and you let it settle down, the water stays at rest until I do something. I'll shake it up a little bit and you can see it move. I did put in a force on it and it started to move. And of course, it eventually settles down because of what? Does anybody know? Raise your hand. Yes, sir. Not gravity.
Friction.
Friction. Except this friction was at this surface. The friction that stopped this water was in itself. It's called viscosity. And in viscosity, it's the molecules dissipating energy as they flow. And we're going to talk about viscosity later in term, but it was known to the 18th century mechanics people, right? Viscosity. It's a kind of friction, dissipation of energy. And that was all very convenient. They were all proud of themselves. Newton claimed to have discovered calculus and all this sort of thing. But there was a problem. In fact, they had a small problem. Oh, I got to do this one. The small problem. And the small problem was actually in this glass of water. They looked at this glass of water, and inevitably, especially in Elizabethan England, water was not exactly pure, there was little particles. And people knew that the problem they had was this glass of water at rest stays at rest, but the small particles never did. They never were at rest. So let's see one. I had a student of mine one time film one. So this is a 2-micron particle at the bottom of a pool of water. It's silica glass, SiO2, and it's just heavy enough that it does fall to the bottom. Its density is about 2. And you can see, and there's another one up to this side, you can see it never stops. What is this called? Anybody know? That's right, Robert Brown. Robert Brown was a Scottish botanist. And he had at that time he had a microscope and he was looking at spores or something like that. And he noticed this, they never sat still. But of course, he wasn't the first person to notice this. In fact, you can go back to the Greeks, as we will in a moment. They noticed this too. And how do you explain it? The water's at rest, the particle moves. So Democritus and his teacher Leucippus, around 460 to 370 BC, noticed this. And he said, well, the only way that this can be explained is that the water is not a continuum. That it in itself is made up of particles also. And those particles bang into the silica particles, and of course, in any instant of time, one side has a few more bang into it than the other side. And of course, that will push the particle the other way. And then in the next instant of time, it goes the other way. That's the only way they could explain it. So they said the universe is composed of void and particles of matter. In fact, they said, this is very interesting, I have an old barn, and it's an antique barn, and there's gaps in the siding. And on a hot morning, the sun's shining through the gaps in the siding in the barn, and you look up and you see a beam of light. And of course, as the beam of light comes through the barn, it scatters light off the dust particles. And they literally, Democritus said, the behavior of these particles of matter is like a, quote, dust mote, M-O-T-E. And if you look it up in OED, mote is a dust plume. Random, and so this is, we're talking 370 BC. They had this picture. Of course, the problem was none of the other Greeks believed them. You know, they got into the earth fire and all this stuff. But they were there, and people followed it. A Roman, Lucretius, 60 BC, he must have had some of the original source material from Democritus. We don't have it. We actually just have the Roman versions of these things. But he quoted Democritus, and he also wrote a poem on the nature of things. They were trying to write, the Romans were trying to write epic poems like the Greeks did. And he wrote the following. Bodies, again, are partly primal germs of things and partly unions deriving from primal germs. See that? Partly primal germs of things and partly unions derived from primal germs. And those which are primal germs of things no power can quench. So here was Lucretius in 60 BC describing what we now know to be elements and molecules. The unions are molecules, the primal germs, elements. Let's go back to this slide. I love this Brownian motion stuff, so let's do a little, show you why I was videoing these things. So this shows a very interesting surface. It's got a surface with a lot of little holes in it, and in each one is a particle. And what this project was about was to make a three-dimensional array of such particles in a high dielectric constant medium. Why would anybody do that? Well, there's a whole field, what's called low observable materials. Low observable, it's the panel that you hang on the stealth fighter that doesn't reflect X-rays. Those panels are handmade composites that have structure inside of them. They create an optical property. And this project was to make a low observable at a much different wavelength so that you couldn't just change the wavelength and see the target. Well, how do you get them in here? Well, one of the ways was to make that structure and put the particles on and just see if they fall in. And you can see it's moving, but let's blow it up. You can see, look at that guy. He's moving along an edge. Doesn't necessarily want to go down in the hole because he's being bounced around by the water molecules. And it's even worse than that in this next shot. Takes a second. Watch this guy. He's in a hole. And he slowly, come on, it's a long lead. The suspense is deathly. Oh, there he goes. Jumps into the next one. So what we found in this is we could never make it perfect because of Brownian motion. Those molecules of water were killing us. We had to do some fancy chemistry. Okay, so things changed though. The big change happened, interestingly enough, in philosophy. René Descartes, 17th century philosopher. He's mostly known for the statement, "I think, therefore I am." You ever heard that? But he was also a scientist. They called them natural philosophers in those days. He wrote a book, Principles of Philosophy, the Principles of Philosophy. He was going to make the definitive book on philosophy. He was an interesting guy, French. He lived most of his life in the Dutch Republic. But he was sort of itinerant. He moved around quite a bit. He had a lot of, in fact, this book, The Principles of Philosophy, was in correspondence. In fact, he dedicated the book to Queen Christina of Sweden, who was an interesting character in herself. She was extremely bright, knew all the main philosophers of the day. She was also a transgender person, if you can believe that, in that time, but publicly known. But she was extremely influential. Any rate, he knew that humans had a tendency to gloss over things like Brownian motion. So in his Principles of Philosophy, the first rule he had, and now all subsequent scientists really obeyed that we'll talk about, is that in order to seek the truth, it's necessary once in the course of our life to doubt as far as possible all things. You have to start by doubting. And then what's interesting, you read through these things, you get down to rule 201. He had a lot of rules. That sensible bodies are composed of insensible particles. that he believed that bodies that we could see were made up of things that we couldn't see. And because of these thoughts, he joined, folks like Galileo and all of those on the Pope's list or index of prohibited books in 1653. And by the time word reached him in Stockholm, he had died. He died at 53 from pneumonia. Actually, because the Queen, it said the Queen got him up every morning at 5 a.m. to talk about philosophy. And he wasn't used to the cold climates in Stockholm and succumbed to pneumonia at a young age. What other rules would we have had? Don't know.